So I hope you're already familiar with the word isomerism or isomers from IGCSE, but just to quickly joggle your memory, let me clarify that isomerism was the concept in which we had same molecular formula but different structure. So we gave many examples back in IGCSE for a same molecular formula but a different structure. And this was the main type of isomerism back there. Now, let me tell you, there were two kinds of isomerism back in IGCSE even. But since most of the books just considered one kind of isomerism, which is what I just defined, we went with that one in emphasis. There was another kind of isomerism which was only applicable to alkenes, and that was based upon position of groups on carbon. But now this space, but this we didn't study in that much detail in IGCSE since that wasn't considered a big example back then. So we actually never gave the emphasis to this one. So we studied this one in detail. To be exact, this is what structural isomerism means. This is not structural isomerism. So what we are going to do in A levels is that we're going to define all these isomerism types, the ones we have studied in IGCSE, whether we studied it with an emphasis or whether we just ignored it being a very small part of it, being a part that has almost less than 1% chance to be a part of exams. So A levels is going to bifurcate these in detail, discuss them in detail, and discuss all possible isomerism types for advanced level, which means these two, as well as more than these two. Okay, so let's get started with structural isomerism, the one where you're most familiar with back from IGCSE, the one that we commonly define as same molecular formula, but different structure, structural formula. Both ways it can be defined, and both ways it's actually correct. Now, we do understand that a molecular formula tells the number of and type of atom in one molecule of compound, and that's actually the exact number. That's not a ratio. Now, propene has a C3H6 formula, 3 carbon atoms, 6 hydrogen atoms, and it's very simple. Because of the simplicity, we can't arrange it in different ways or types. For example, if I do take the example of propene and I discuss the example of, let's say, um, butane, I'm taking an cane intentionally. Now, the structure can be drawn this way. We do understand it can be a straight chain. This can be it. Now, I hope you understand this is the easiest way of drawing butane. C4H10, we can also write it like this, CH3, CH2, CH2, CH3. Now, the other way was to do this is to draw it somewhat a little bit differently and actually to go with a branch structure. Usually, the way that this differentiates is a straight chain structure or a branch structure. If you count, both of them have 4 carbon atoms and 10 hydrogen atoms each, but they have different structures. So they have the same molecular formula, they have different structural formulae. Okay, when I say the word different structural formulae, obviously the displayed formula is going to change too. Okay, I drew the displayed formula for the one on top, but I never drew it for the one at bottom, and I hope you can draw it yourself. Now, moving on, this is structural isomerism, which means you can draw them differently with a different structure, and we still have the same molecular formula. The book caters the example of C3H6. This is an alkene, and this is a cycloalkane. Now, I hope you understand that the book is purposefully going with these examples and actually putting up the idea of having the same molecular formulae for the same number of carbon atoms for a cyclohexane or for an alkene. Okay, that's how C3H6 can give us this one as well as this one. So it gets us the idea. Now, we are really going to define this kind of structural isomerism into different types. Let's go through those types. There are three major types, although there are more, but at A level, we keep it short to three different types: position, functional group, and chain isomerism. Let's start with position first. Position isomerism. It's very simple. The location of functional group varies in each isomer. And that's pretty simple. Take a look at these examples. This is an example of position isomerism. All of them are, if you look at them, C3, H6, Pr2. How would you know that this is actually a position isomer? Okay, the definition is pretty easy, but that doesn't give us the idea how we are going to cater these kind of questions specifically for paper one. So I'm about to give you a few tips which might not be a part of the book. So first things first, as soon as you look at it, they all may seem the same for the number of atoms or the type of atoms they have: 3 carbons, 6 hydrogen, 2 bromine. How would you know that this is not just a repeating structure, right? But another position isomer. Now, the easiest way is to name them, and if their names come out to be different, they are position isomers. Now, their names are not exactly going to be completely different, but because of the position, the numbers might change a little bit. Okay, let me clarify. Now, let's go with this numbering: straight chain, 1, 2. This is 1,2 dibromopropane. Okay, and I am going to write the name so it gives you the better idea of how it is going to be. Now, I hope you already understood the fact that they are all going to be dibromopropanes. It's just the difference of numbers that is going to happen every time. The dibromopropane part is going to be the same. So whichever side I start numbering from, I end up with 1,3 dibromopropane. So the rest of the name is same. If I go with this one, of course, I'm going to give it 1, 1, and this one, 1, 2. So I am going to write it as 1, 1 dibromopropane, and this one as 2, 2 dibromopropane. Remember, now, something to clear up the confusion. 3, 3 dibromopropane this one cannot exist. One important point. Now, can anyone answer why 3,3 dibromopropane cannot exist? Or how is it a wrong name? Now, if you understand this point, it would be very easy to actually clear your confusions in an MCQ paper and answer them correctly. Anyone? Come on, this should be easy. Since you have studied the rules of nomenclature with me, you can easily tell me that why this is a wrong name, or why this name can be corrected into a name we have already considered in these four examples of position isomerism.
You're asking for 3-3
Yes,
diagram.
yes, I am asking about 3-3, and I'm specifically saying it does not exist or it is actually a wrong name. Now, I'm asking you the reason. Can you tell me why? What would be the reason why this would be a wrong name or why it cannot exist? Okay, let me number it for you. And this time I'm going to use a different color for so that it's easier for me to explain. Now, if I number it 1, 2, 3 this way, in that case, the bromine has to be here and here instead of hydrogen. Now, if the bromines are here, I'm supposed to start numbering from this side. So actually, 3,3-dibromopropane uh, can exist, but that won't be the right name. The right name would be then 1,1-dibromopropane. And that already exists. This is 1,1-dibromopropane. In a similar way, 2,3-dibromopropane would not exist or is a wrong name, right? Just take a look at this.
It will be 1-2, right?
It would be 1, 2, because 2, 3 won't be a good name, way of naming them. That would be actually incorrect. These are not the rules that we have been following. So it can't be 1, 3. It has to be 1, 2. So this is the right example of doing it. So actually, all the possibilities that you come up with for position isomerism may not be the correct ones. Now, how this question can be twisted in A-level exam, there are different ways. Now, the first and more common way that you can think of right after this example is that the structures like this would be drawn, and they might ask you to point out an incorrect structure. Or apart from these four examples, you already have a structure up top and you need to find a position isomer for it. Now, you can only do it correctly if you understand what kind of position isomers would exist and what kind of names are actually wrong names and those won't even exist. Now, that's the purpose behind it. Another way of asking this question, which actually makes it more difficult, is to talk about how many position isomers would this structure would have. They would simply give you the formula and they would ask you total number of position isomers. And let me tell you, the total number of position isomers for this one are 4, and those 4 have been drawn over here. There are no other position isomers. Position isomers. Now I'm being really specific. I'm not talking about structural isomers. Okay, that changes the whole story. Structural isomer is a bigger, broader term used for all kinds of isomers. Right now, we are just talking about position isomer, which specifically means that we can position the functional group, which in this case is the bromine atom, at a different position. So yeah, they're positioned differently. 1, 2, 1, 3, 1, 1, and 2, 2 give us the idea that these four would exist. Now you need to carefully consider that 3, 3 may come across your mind, but that won't be possible. Mathematically speaking, this can be a probability. Chemically speaking, as per the rules of nomenclature, this is a wrong way of naming. All right. So mathematically, if you can come up with many different possibilities, but not all of those possibilities are going to be correct. See, when you look at the formula, you think there are 2 bromine and there are 3 carbon. So there must be carbon 1, carbon 2, and carbon 3. So I can put 2 bromines in different ways. So I can put them on 1, 1. I can put them on 2, 2. I can put them on 3, 3. So I can put them on 1, 3 and 1, 2 and 2, 3, right? These are all the probabilities that you might think of. But that's what I'm saying. Mathematically speaking, this might exist as a probability, but chemically speaking, they're not correct. Now, does that make sense to you?
Yes.
Now, you do understand that you sometimes need to calculate the total number of position isomers for any given formula and for any given formula, and you take the possibilities out based on mathematics, not in chemistry, but you judge them on the basis of chemistry. ये जितनी 6 possibilities लिखी हैं मैंने mathematically calculate किए हैं based on the simple probability rules, right? But I then judged them chemically and then came up with my answer. So all of the mathematical probabilities were not correct. ये आपको MCQ पेपर में करना पड़ेगा. So you need to be very vigilant when you're going through this, and you can only do it correctly if you're good with the naming rules. I think I've made my point. So let's just move to the next part. The definition seems in the book seems very easy, but it's the past paper question which makes it difficult. It's actually the way how Cambridge manipulates the whole question which makes it difficult. If you just read through the book, you'll find it extremely easy. Yeah, it's a very small definition, two different possibilities of, since there are two functional groups, there are two different possibilities. There you go. You go ahead and you understand, yeah, it is the same thing. It might not be the same thing. Okay, so that's how it happens. Now, one very important thing, uh, and I am going to specifically, just a second, this one, sorry, my bad. This line, okay? Remember, there is free rotation about carbon-carbon single bond. Now, this specific line gives us the idea and the leverage of writing any atom at any position, but at the same time, this gives us the boundaries of judging them on the basis of chemistry, whether they are right or not. Now take a look. If we draw this bromine on this side, or we write it over here, it means the same thing. It still is one bromo, or it still is present at position 1. This one at position 2, this one at position 1, or this one at position 2, this one at position 1, this one at position 2. They're all 1,2 dibromopropanes. Now, free rotation means that if some students write bromine over here, another one write over here, another one may write it over here, right? Since you can rotate the bonds freely in carbon-carbon single bonding system, they all would be considered as one bromo, which means you have the leverage to write them at any position you want to around the same carbon atom. Plus, you may rotate the structure like this. It would still be the same. This is the trick that we have discussed before. While I was going through the nomenclature part, I was telling you the trick. This is the trick. I told you that we can rotate the structure, but you still need to locate the straight longest carbon chain, and that's how we locate it. Now, this is the straight long carbon chain, 1, 2, 3. That's how we number it. I hope you get about idea about this one. But the point I'm trying to make over here is that bromine can be written anywhere in this on this carbon atom 1. A student might write it up top, a student might write it at the bottom, a student might write it on the left. All three students are considered to be correct because there is free rotation around carbon-carbon single bond, which gives you the leverage of writing it anywhere, but which also gives the examiner of manipulating it in multiple ways. If you have the leverage of writing it anywhere and getting the complete marks, the Cambridge examiner also has the leverage of rotating it and making the question a little bit more difficult for you. So that's why you need to be vigilant. I hope this point is also clear. If it is, we can move forward to the next uh, type.
Yes, sir.
All right, that's great. Function group isomerism. Now, as the name suggests, it's completely understandable that the isomerism is between two entirely different functional groups. Now, you might not be familiar with the functional group on the right. I hope you understand that you're familiar with the alcohol function group and this OH with the name or the suffix of OL. But the other one on the right hand side is an ether, which is basically an oxygen bonded between two different carbon chains, carbon chain on the right, a carbon chain on the left, and it's named in the way of writing oxy between the both chains, meth and eth and oxy between one of them, methoxyethane. All right. So we don't exactly need to go with this kind of naming, but you should be familiar that ether is a functional group in which there is an oxygen right between two carbon chains, and we usually write the word oxy between the both names. That's about it. That's all you need to know. Apart from that, apart from the information of the ether, functional group isomerism is pretty easy since some functional groups always lead us to the same molecular formula, but a different structure based upon a different functional group entirely. Now, if you take a look at it, this must be C3H7OH in both the examples. You'll count the carbon atoms to be 3, hydrogen atoms to be 6, uh, a total of 7 actually, a total of 8 actually, sorry, and one oxygen atom. So this like something like this, but if I sum them up, this actually is C3H8O. But either way, it's fine. Now, writing this way of formulae actually means cumulatively writing all types came out from functional group isomerism because this is the way we write ethers in order to specify this oxygen. This is the way we specifically write alcohols in order to specify the OH part, but this is the way we can write them cumulatively. So usually in exams, when they write something like this, they want you to understand they are going with a bigger, broader term, and they might confuse you later on with any of the functional group isomerism-based isomers. I hope you get my point.
Yes.
Good. If you do, let's move on. Basically, the isomerism itself is easy. What needs to be explained at this point, and what I'm trying to do all along, is to give you the idea that how Cambridge manipulates the question, because that's what you are going to see first in Cambridge exams. And the questions I have been talking about really are not the theory questions. This is mostly intended for paper one instead of paper two. However, there can be questions in paper two related to this part as well. Finally, chain isomerism. Chain isomer is different in the structure of carbon skeleton and actually the chain. Whether the parent chain is of the same carbon number or parent chain has been broken down into multiple branches or single branch and since then gets smaller. So if you look at both of the examples, these both are C4H10. The example I actually started off with when I was explaining the isomerism back from IGCSE. And now you understand if we take that example from IGCSE and if we put it, you do get the idea that this example is for chain isomerism. Now, if I go back, I hope you're clear with chain isomerism, right?
Yes.
Okay. Now, before I go back, actually, I need to put something out there. Okay. Methane is such a small structure that you won't be able to come up with isomers. So is ethane, so is propane, right? You won't be able to come up with isomers. When you come to butane, you have two isomers. When you move on to pentane, you're going to have approximately three isomers. Moving on to carbon 30, sorry, moving on to carbon 30 based alkane, the number of isomers are actually around somewhere around 4 million. All right. So
4
with
million.
every, yeah, 4 million. That's why organic is such a big brand. And when we say number of isomers, there's actually all kinds of isomers. The chain isomers might have a smaller count than that, but even that count would be big enough to amaze anyone. Now, the number of properties of how you can arrange the number of ways, sorry, not properties, number of ways how you can arrange those carbon atoms is going to have a huge number, means we can arrange it in so many different ways if the number of carbon atoms keeps on increasing. So that's why for now, we have theoretically considered around 4 billion compounds in organic chemistry alone, but experimentally, we are yet to consider many compounds, out of which 40 million have been worked upon by humanity, and they're still working upon the rest. So organic chemists have a long way to go. And I hope this is just alkanes. I'm not considering any other homologous series. Since I'm just talking about alkanes, I haven't yet even considered alkenes or alkynes or other homologous series. So the possibilities for organic chemistries are way too much. We are talking about much more than billions. Okay. Um, Now you see both the structures. What do you think this type of example is? Now, chain, position, and functional group isomers are all examples of structural isomerism itself. C4H10 was an example of chain isomerism. I just considered that. What about this example, C3H6? You see one structure for C3H6 over here up top, this one, and you see the same C3H6 over here. Here it's an alkene, and here it's a cycloalkane. So which category do you think it falls in out of position, chain, and functional group isomerism? Since I've explained it
Functional
already,
group.
right, functional group, very good. So it's functional group. Why? Because cycloalkanes are a different functional group and alkene is a different functional group. These functional groups are actually separated on the type of bond, not because of the presence of any other third atom or a group of atoms. Okay, since I've been going through the organic discussion before, so that's why I'm posing questions to make sure you understand those organic points when I use organic terms. I hope you're clear about this. Now let's move
Mm,
on. The other type of isomerism, stereoisomerism. Now, when I was quoting the example of IGCSE, I quoted you the example of alkenes, and I talked about that the arrangement of the atoms or group of atoms that are connected to the doubly bonded carbon atom in alkenes at different positions. And we never considered it as a part of isomerism. We called it a different kind of isomerism. Now, that kind of isomerism actually falls under the category of stereoisomerism. Since stereoisomerism is a different type, let's consider this one out. Stereoisomerism are compounds whose molecules have the same atoms bonded to each other, but they have different arrangement of atoms in space. Now, this different arrangement of atoms in space is something that needs to be explained. So I'm not going to explain it right now. Instead, I'm going to move on to the other two types and take examples, since this can only be explained with examples. Let's start with the types. There are two types. The first one is geometrical isomerism. We also call it cis-trans isomerism. The second one is optical isomerism. Now let's move on. Cis-trans isomerism. After doing cis-trans isomerism, since that's the alkene part and the atoms bonded on to the doubly bonded carbon atoms of alkenes, I hope you get the idea. The previous type I was discussing for an example out of IGCSE was actually symmetrical or cis-trans isomerism. So, unlike a carbon-carbon single bond, there is no free rotation about a carbon-carbon double bond. कार्बन-कार्बन double bond में कोई free rotation नहीं होगी, ठीक है? Just a minute, let me get a glass of water. So there won't be any free rotation about a carbon-carbon double bond. Okay? You cannot just go ahead and put the atoms wherever you like, because if you're going to do that, you're going to result in a different isomer. Now, previously, when I was discussing, when I was discussing the previous part, this one, putting this bromine atom, and I'll be really specific, putting this bromine atom over here, or if you put it over here instead of this hydrogen, you put hydrogen over here, or you put this bromine over here and put this hydrogen over here, it does not matter. It would still be one bromo, right? And if it is one bromo, really the position of the position of bromine on the carbon atom, because of the free rotation, does not matter. And it does not result in a different isomer. However, on a doubly bonded carbon atom, since there is no free rotation, it does matter what that is. Let's clarify by taking the examples of carbon-carbon doubly bonded compounds, and that's what we are going to call as geometrical isomerism. Now, geometrical isomerism is a pretty straightforward kind of isomerism. There are two types, and we define them as cis type or trans type. Now take a look at it that both of them are 1,2-dibromoethene. 1,2-dibromoethene. Eth means two carbon atom, ene means they are doubly bonded. Now, if you take a look at it, you'll understand that the cis is based something like this, same atoms, and the trans is actually based like this. Okay. Whenever we define these, we define it in the almost a similar way. We can define the transfers. The atoms, the same kind of atoms are present on the main diagonals. Now these cross signs that I drew on top of the atoms, they're actually known as main diagonals or doubly bonded atom based diagonals, carbon-carbon double bond diagonals. Okay, that's how trans goes. And if they're not present on diagonals, instead they are all present on top and bottom, they are actually cis. That's how it goes. Make sense?
Yeah.
Now, it's the position of this bromine on carbon atom. And if it's over here, this would result differently. It's over here. Now, if you take a look at this, I am going to erase everything in order to explain what I'm about to do now. If I change this bromine over here and take the hydrogen over there, it becomes trans. That's how it is. Picture this, bromine over here, hydrogen over here, it becomes trans. So if I try to change the position, like what I was doing back in alkanes under the name of free rotation, right? There is no free rotation in carbon-carbon double bond. It actually changes the whole isomer. Back there in alkanes, there was no change in isomer. Here, it is a change in isomer. Now let's clarify. In cis-1,2-dibromoethene, both the Bayer atoms remain fixed on the same side of carbon-carbon double bond. That's how you're supposed to write it. Same side of carbon-carbon double bond, cis. All right. However, in trans, they're positioned across the carbon-carbon double bond. You may also write it across the diagonals or main diagonals of carbon-carbon double bond to make it more specific. Both ways, if that's written like this, would define trans isomerism. Okay. And they have been talking and explaining the prefixes as well. Now, the book is about to explain the way these questions can be manipulated, and also the book is about to explain the possibilities of stereoisomerism or specifically symmetrical isomerism. Now, we have discussed the possibilities back for structural isomerism. Now, the possibilities for this one are to be understood with a lot of vigilance because this is going to define how you're going to do everything. Now, there are some points mentioned in the book. Well, there are some points that are not mentioned in the book. So, for the points that are usually not mentioned in the book, I'm going to take different examples to make sure you understand the whole point. Now, starting over this paragraph, the two stereoisomers have different arrangement of atoms in space, different compounds, different physical properties. Now, this gives you the idea about why just trying to rotate it free turns into a different isomer, and what happens if we have a different isomer. Try and get the point. They're different compounds with different physical properties. Even the appearance can change. Just moving the bromine and hydrogen up and down, you might think nothing would happen, but they might have an extremely different set of physical properties. And when we are going to talk about medicinal properties, which we're not going to do in this part of the book, specifically in AS, which we are about to do in A2, you'll understand they might have two entirely different medicinal properties. Let me tell you that a doubly bonded compound may have been a medicine for a cis compound and may be a poison for a trans compound. The examples are given in A2 part of the book. This is how different they can be. All right. Did you get my point?
Yes.
That's how different they can be. Okay. So stereoisomers can also have different chemical properties, can also have they tend to have same properties, but they may have different properties. Now, that is not a must, but for physical properties, this usually comes as a must. Okay, that's why these sentences are written like this. So whenever they are going to talk about the difference, do not prefer chemical difference. You're supposed to prefer the physical difference first, because that difference is a must, right? So moving on, for example, they may react at different rates for the same reaction. Whenever we have unsaturated compounds with the structure shown in 14.23, we can have this geometrical or trans type of isomerism. And the example given over here with 2Br and 2Hs is extremely easy. That's not all what we have to face. Let's consider this one first. Now, if you look at it, these are two carbon atoms, and these are four different atoms or group of atoms. Let me tell you that they can be as different as fluorine, chlorine, bromine, and iodine. This can be entirely different. H, CH3, Cl, C2H5. Okay. I hope you get my point that A, B, E, and D represent entirely different atoms or group of atoms. When this happens, we clearly understand we have three different types that we might need to deal with at advanced levels. And I hope you understand that AA and BB was the type that you just went with H's and PRs. And that was actually an easier type to go with. If you introduce one more kind of atom, it becomes AA and BD. If all four are different, that is when we have AB and ED. Get the point?
Yes.
Okay. Usually, now, so far, it's pretty easy to understand that there can be different atoms, but how would we know which one is cis and which one is trans if this is F, this is Cl, this is Br, and this is I? How would you know which ones to position at diagonal and which ones to position on the same side of the double bond? Since it was pretty easy with H, Br, and Br, now you know they're at the same side, switch the sides, you'll get the other kind of isomer, right? So if this is one type of isomer, how would you switch sides? How would you know that if this one is a cis one or this one is a trans one? Difficult, right? We need to come up with
Yeah.
at least one way of bifurcating it before we can come up with the other isomer. So usually the easier way that we bifurcate it with, even if they're different, is the MR values. Smaller MRs on one side, cis, bigger MRs or bulky groups on the other side, trans. This is just one way of doing it. One easier way that we usually apply at this level so that the students can easily, comfortably can define the cis bonds and the trans bonds. Get the point? MR is a generic term. It might be a single atom and you might be using AR, relative atomic mass, not exactly MR. Make sense?
Wait, so how do we decide it based on the MR?
So if CF and CL, since these are the least mass, right? They are on the same side. This one is cis. Switch any one of the sides on the right or the left, they will become trans. So if I write it exactly
Oh,
as trans, this could be something like this: Br, F, Cl, I. You can switch any of the two sides. Okay. By switching, I mean to switch these sides, this one over here and this one over here. So you can either switch the entire left side or you can either switch the entire right side in order to get the other isomer. Switching any side would work the way. Okay. Switching
mm,
any side would work it because now they would be facing different atoms on the other side. If I switch F and Br, look, F and I at the same side. If I was supposed to switch Cl and I, of course F and I would be at the same side there. Make sense? Let's do it like this. F and Br are still on the same side. I never switched it. Now I'm going to switch I and Cl. Take a look. It is still the same thing. Fi and I on the same side, Br and Cl on the same side, Br and Cl on the same side, F and I on the same side. That's what I'm talking about. So either you switch the two atoms of group of atoms on the left or you switch the ones on the right, you would get a new isomer. But switching them both at the same time, you are still back to a cis isomer. I hope you understand 2 times switching means you're back to the same isomer you started off with. Do you get the point?
yes.
Good, good. Now, these things are important to understand before you start making mistakes. Now, I am going to tell you something which is not a part of the book, but it is going to make a lot of MCQs easier for you since that has been a part of paper one way too many times. Let me clearly say that this, whatever this is, I'm not even talking about the other sides, is not a cis trans isomerism. Okay? Since two same atoms cannot be present on the same side or either on the right or on the left. If you have two same atoms on the right side or on the complete left hand side, this is not geometrical isomerism at all. This doesn't even stay under the category. Okay, get the point? For example,
Yes.
if I have this H and BR, this is not exactly symmetrical isomer. This does not even fall under the category. Or even if one side is same, it won't fall under the category. So by giving you this specific example, the point I'm trying to make is sometimes they do write the structures like this and then go on with writing the whole formula. It won't be a cis transfer or geometrical isomer if it starts with CH2 for the doubly bonded carbon atom, because that means there are two hydrogen on the same carbon atom. And if there are two same elements on the carbon atom, it's not a geometrical isomer. Makes sense?
Yes.
That's an easier way to point out the substance that might have been an option of a question, but does not fall under the category of cis-trans geometrical isomerism. Now, there is also geometrical cis-trans isomerism possible in substituted cyclic compounds. Okay? This is because of the limited rotation about carbon-carbon single bonds that make up the rings. रिंग्स के अंदर सिंगल बॉन्ड्स पर ही पॉसिबल होता है उनके अंदर रोटेशन होती है लेकिन फ्री नहीं लिमिटेड होती है we usually show the cis and trans isomers using a combination of skeletal and 3D formulae वो शो किया हुआ है इनसाइड जो है वो skeletal है आउटसाइड आप देख रहे हैं कि वो 3D formula है तो cis 3-methyl cyclopentanol and trans 3-methyl cyclopentanol have been shown. And this gives us a very good idea that how they are actually supposed to look like. Now, if you take a look at this, I'm talking about this one first. Outside of the plane, right? Outside of the plane, this one. One is outside the plane, one is inside the plane, or pointing inner or away from you, towards you, away from you, towards you, away from you, something that I tell on the cinematic sense of view, right? So you get the point. That's why trans and cis. Now, what is actually happening is that there is also a hydrogen atom attached to this carbon. Since this is a carbon atom with single bonds on two different sides, so it is supposed to have two different groups or atoms or group of atoms. So it is between methylene hydrogen and hydroxide or hydroxyl and a hydrogen. So take a look at it. Both are pointed outwards, and of course, both are pointed inwards. One of them is pointed outwards, one of them is pointed inwards. What we do usually, now they are pointing them out of the paper as upwards and in the paper as downwards. This is another way to show it. Now, these kinds of examples actually increase your perception of organic chemistry or how we usually quote things. Now, naming is not the only thing that you need to learn when it's about organic chemistry. There are many more things that should make clear sense to you. Out of those, there are 3D rules. Now, in 3D rules, I hope you understand the wedges, dotted lines, or dashed lines. Apart from that, for cyclic structures, when we draw them like this, the one upward and the one downward has a meaning. We're not just showing them as we wish to. There is a sequence, there is actually a synchronization of sequence that we follow. So the one that is upwards is going out of the paper, and the one that is pointed downward is going into the paper, away from you or towards you, irrespectively speaking. ठीक है ये बात समझ आती है
Can you repeat it once again?
Okay, the point I'm trying to make ये एक cyclohexane है let's suppose ठीक है अब इन्होंने जानबूझ के इसे इस तरह शो किया हुआ क्योंकि इन्होंने यहाँ पर लिखना है दिस इज ऑल्सो पेंटागन, दिस इज ऑल्सो पेंटागन. Now, if you write something over here and something over here, on top and at bottom, मर्जी से नहीं लिख देना है. Top means upwards, ठीक है, and upwards is actually out of paper, ठीक है. And out of paper means कि जब आप इसे 3D मॉडल से बनाएंगे तो it would be a wedge, right? I hope that makes sense. और जो downwards होता है, ठीक है, there is a way we do things in organic chemistry, and organic chemistry is actually difficult because you need to understand the systematics. Once you do, it's not difficult anymore. Now, this is in the paper. Yeah, into the paper, we write it many ways. Take it towards you or away from you is another way of doing it. And we either do it with a dotted line or we do it with a dashed sign. Both of them work the same. So this is what it means. ठीक है, ये सिर्फ वो ग्रुप्स जो डाउनवर्ड हैं वो शो किए हुए हैं. इंटरनली एक हाइड्रोजन होता है जो उसके साथ मुकाबले में आ रहा होता है. The point I'm trying to make is CH3 and hydrogen are to be seen appropriately. Now this is cis because दोनों हाइड्रोजन एक तरफ हैं और दोनों OH या CH3 एक तरफ हैं. ये ट्रांस इसलिए है कि ये दोनों डायगोनल पे हैं और ये दूसरे डायगोनल पे हैं. That's why they are known as cis trans. Notice करें, both the hydrogens are downwards. तो हमने इसे क्या कह दिया? Cis isomer. Now one of the hydrogen is downward and one is upward. हम इसे क्या कह रहे हैं? Trans. Let's suppose अभी आपको out of the paper या in the paper समझ नहीं आता, लेकिन upward or downward तो definitely clear है as soon as you see the diagram. And I'm gonna erase it for you so it's easier for you to see the diagram. Now, I think now it's pretty obvious. कि अपवर्ड्स और डाउनवर्ड्स से बहुत बड़ा डिफरेंस आ जाता है. क्लियर इनफ?
Yes.
ग्रेट. Another example of substituted compound of cyclobutane with two groups substituted into four-membered ring, four corners हैं, four-membered ring, ठीक है. Two geometrical isomers below are cis and trans isomers. To be exact, cis cyclobutane 1,3 dicarboxylic acid, ठीक है. अब ये नाम आपको देखकर थोड़ा समझने की जरूरत है. साइक्लो मीन्स स्ट्रक्चर साइक्लिक होगा, पहला और आखिरी कार्बन एटम भी बॉन्डेड होगा. ब्यूट मीन्स 4 carbon atoms in total. Ane means singly bonded. 1, 3 are positions. Di means 2. Carboxylic acid means COH group. So 1, 2, 3, 4 carbon atoms and 1, 3 पे हमारे पास COH है. Again इसमें cis trans isomers क्यों बने? ठीक है, H H H H. ठीक है. Are we clear? Since this is exactly similar
Yes.
to the example above, it's just that the cyclocomponent is different. Instead of talking about a cyclopent, we're talking about a cyclobute PC over here. But for the rest, it is the same. ठीक है. अब इससे कंफ्यूज नहीं होना है. बच्चे मुंह में पोजिशन होते हैं कि ये इनवर्ट ड्रॉ करना पड़ा है, ये भी इनवर्ट ड्रॉ करना पड़ा है. No, that's not it. These both are wedges, which means these both are dotted. Now both of the hydrogen atoms are dotted. Now this one's dotted and this one wedged. It means कि ये वाला hydrogen dotted है और ये वाला hydrogen wedged होगा. And which changes the whole story about cis trans. तो ये cis trans है. ये cis है, same. ये trans है क्योंकि इसमें दोनों ग्रुप्स डिफरेंट हैं और हाइड्रोजन भी डिफरेंट है. उनमें दोनों हाइड्रोजन एक जैसे हैं और दोनों ग्रुप्स भी एक जैसे हैं. Same side of carbon, doubly bonded carbon atoms, or in this case, cyclo system, or ये भी different sides of cyclo system. I hope you get the point, right?
Yeah.
Good. If you do, We are done with cis trans. There is still one more type left out of stereoisomerism, tier 2 type. Cis trans is geometrical. The second one is known as optical. We are supposed to go with optical after this one, but I think it's good enough for today. If you have any questions, you can ask me now.